In terms of what we're talking about today is that we'll do some review about what we discussed last time, which was some of the introduction aspects to Gaussian mixture models. And then we'll delve deeper into basically an optimization algorithm, expectation maximization. We'll talk about how exactly this is applied to Gaussian mixture models. We'll talk about a much broader view of expectation maximization because in particularly E&M, it's very powerful, can be applied to a wide variety of mixture models, probabilistic graphs, etc. So after kind of talking about a more general look at expectation maximization, we'll kind of go into some additional applications of E&M. So we'll talk about some other mixture models outside of just Gaussians. We'll talk about its application to some Bayesian regression. And then we'll probably end, depending on my pace, around doing E&M on basically mixture of experts is what's referred to, but basically mixtures of Bayesian regressions. So we're going to kind of jump slides here. Let's see here. Okay, so Gaussian mixture models. Really powerful model. In this case, just to remind you, is that the idea is that we're kind of doing unsupervised learning here. So the idea is that I just have some data, I have some features, and essentially what I want to do is that I want to try to extract groups of them. So I want to try to segment this data to the best of my capabilities, to hopefully just withdraw some useful information from that. Now I don't know how many classes there are. I don't know what the right number of classes are. So it's up to the algorithm to really figure it out. And just to remind you, this is the reason why we call it unsupervised learning, because we don't actually have class labels in this case. The supervised version is if we knew what each class was. And we've done a lot of supervised learning. But in this case, we don't actually have that information. So we're trying to pull some structures from the actual data. So as the name implies, Gaussian mixture model, it uses Gaussians. And we use them a lot because they have a lot of nice properties. Being an exponential family makes them very easy to manipulate and work with for inference and all the good things that we need to do. So starting off with an example, you guys have already seen this slide, of an example of a Gaussian mixture model. In this case, I have three particular Gaussians here. So red, green, and blue. And basically what I'm doing is I'm fitting this data down here. And you can see that the actual, so if I combine all the Gaussians, that I end up with this very unique looking distribution. Although the mixture of each independent component is relatively simple, we can form a very abstract, very nonlinear, very organic looking distribution that fits our data relatively well. So let's just say before we talk about training a Gaussian mixture model, so in terms of sampling a Gaussian mixture, the idea here is pretty straightforward. The first step is you say, okay, so in this case I have three Gaussian mixtures, again, red, green, and blue, and you start off by sampling the actual mixture component, so the actual class. So if each of these are given an equal probability, right, so like 1/3, I roll a three-sided die, whatever it lands on, I pick that Gaussian, so like let's say I roll on green, and then I go and I sample from that Gaussian. And I repeat that again, maybe sampling from blues, sampling from red, on and on until basically I draw on multiple samples in multiple classes, and then I end up with kind of the total sample space that the actual Gaussian mixture spans. So, as kind of discussed here, an interesting application of these mixture models is actually on, we'll kind of revisit this in more detail and make this a little bit more clear, I believe, is actually the application to an inverse problem. So the idea with the inverse problem is that one particular input may have multiple outputs. So rather than kind of a standard function where we kind of have this bijective mapping of we have one output to one input, the true solution is just a one-to-one mapping. The idea here is that we have an input, we may have 3 potential solutions. We may have 4, we may have unknown potential solutions. And it just so happens that these mixture models and they tend to be pretty good for doing these type of problems. So yeah, just read here. Colors and yeah, that's all I really want to talk about. That. So yeah, and this comes back to of the idea of unsupervised learning here, is that this kind of the supervised or the complete data is that we have the classes for each. We know what points belong to what specific component in the mixture, and like the true unsupervised problem or almost the ill-posed problem is essentially we don't know anything, so we don't have any idea where these points are being drawn from, what the distribution is, and we want to figure out what the best way to actually model that. An important viewpoint, which we'll deviate from a little bit, and then we'll come back and revisit it in the context of E&M, is the idea of the use of these latent variables. So kind of idea is that we have these, in terms of the Gaussian mixture, what we're going to do is that we're going to utilize a binary latent variable that essentially acts as a switch, right? So these latent variables are telling me which component our actual data belongs to. And these will end up, while we'll kind of, the more kind of intuitive way to view these is that these are more, mixing parameters or mixing coefficients. Well, Z's aren't, but others are. But the idea of representing mixture models in the concept of a latent variable model where we have some Z and we have the actual observation here is very important. And it's also very important in the application of E&M because, as you can guess, this type of representation can span far beyond just Gaussian mixtures. So it just so happens that Gaussian mixtures fits into this latent variable model. But this is actually a very diverse set of machine learning models. So in the context of this, though, getting back to Gaussian mixtures, the idea here is, again, we have kind of a binary switch. So if RGB are like our 3 classes from the previous slide, you can see that essentially we just have 1 is on for red, so this means it belongs to maybe class 1. Similar for class 3, class 2, etc. And each one of these in here would be like your data points. So that's kind of the philosophy of this particular latent variable here. So again, the Gaussian mixture distribution, which we saw in the previous slides. So we have our standard Gaussian here, and then we have essentially these mixing coefficients. And just looking at this, we don't really see a latent variable in here at all. However, it's kind of implicitly in there, in the sense of essentially we can introduce it by means of basically kind of indicator functions. So again, this was on the previous slide. Again, these are mixing coefficients. So by definition, we know with these mixing coefficients that they must sum up equal to 1. And we can see here is that actually this latent variable that we're introducing, we could actually express the likelihood of it as basically a categorical distribution here. So we have each class, so K classes, right? So K is the class index. So that means, so for every single class, we have a mixing coefficient, and we have a mean, and we have a covariance matrix. So the actual probability of a particular Z, so of a particular class, is essentially the product of the mixing coefficients to the power of this binary variable. And this is basically overcomplicating things, but this is this like a rigorous mathematical way. If these are binary, essentially the probability of Z belonging to a particular class is actually just literally this mixing coefficient, right? Because either this is 1 or it's a 0. So it's just going to be whatever pi of k for whatever particular k you're concerned of, which makes sense, right? That's what our intuition would tell us. So, so now if we kind of introduce these latent variables here, we can now represent, so we have a joint distribution of, so we have the conditional. So we start with the conditional distribution of our data, so our actual features. We have our Gaussian, and given a particular z. So now you can see that the z, similar to what we had on the previous slide, so the prior distribution of these latent variables, is also basically up on the actual likelihood here. So essentially, this is again acting as just like an indicator function. If x belongs in a certain class, or we want the probability of x belonging in class 1, this z is only active for zk is equal to 1. It's 0 for everything else. So naturally, this just turns into the evaluation of the Gaussian for that particular class. So combining them together, we can get the joint distribution here. So we have the conditional times the prior. And then you can see that we pulled out this latent variable here, and we have the resulting product. So very straightforward, very intuitive, and as we kind of show here is that if you marginalize over the z's, right? So if we just sum over the z's, we have a finite set, so we don't have to do anything analytical. So we just take a summation over the z's. You can see that expressing this in terms of like a mathematical sense is that these are, like what I said, these are just indicator functions, and we actually end up back at our original mixture distribution that we started with. So we can see that we're fully consistent here. And the question is, well, okay, what's the point of introducing these z's? If I end up back in the same spot that I originally was, why bother? And the answer to that is essentially using the joint leads to a lot of simplifications in terms of actually doing inference on it. So, some not necessarily jargon, but some technical terms regarding mixture models. The responsibility of a particular component, so there's a particular class, is basically explaining, so the responsibility of a particular component to explain a specific observation is basically given as the following. And the idea, so gamma, so this is a responsibility, is essentially it's the probability of, given this observation, what is the probability that it belongs in a particular class. And intuitively, the result here is, it's very straightforward. Essentially, this is right here is the probability of it belonging to a particular class divided by the probability of it belonging to all classes. And fundamentally, that makes sense. So down here, we can see what exactly this responsibility actually implies. So again, we have kind of this 3-component sample here. So again, this is like the complete data. So this is, I know the classes. So I have the 3 specific classes that I'm drawing each data point from. I have, in some sense, this can be considered the joint here. So this is the P of X and Z. Over here, this will be the actual data that you would be training the model on, which is the incomplete data. Essentially, I just have P of X. So I just have all these belong to some X amount of classes. I don't know what they are, but this is the data I'm getting it in. And over here, so after we train some model, these are basically responsibilities. And you can see that this is modeled by a transition of color. And so you can see that some points, some of the points that although, we sampled them in between, to sample these, maybe they were sampled from one class, maybe they were sampled from another class. On these buffer regions, these mixing regions, is that we can see that the responsibility is actually being shared by 2 specific components, and that makes sense because each one of these Gaussians are basically they're sharing this sample space here. So plotting data in this sense can actually reveal a lot of intuition about how the actual mixture model is functioning. Okay. So the law of likelihood here. So the law of likelihood function of our mixture model is essentially the following. So again, we have the distribution, our mixture distribution here. So P of X, mixing component, our likelihood. We have n data points. Okay, so n is the data, k is the number of classes. We've taken the log of it, And basically what we've ended up with is that we have the log of a summation. And basically at that point we've hit a dead end. So we can't do any further simplifications. Ideally, right, the ideal solution is that we get this log inside, right? That's kind of our just intuitively what we've seen in the past, that's what we want to do. So we want to get it inside, we want to get it into this pi and operating on this normal distribution. Because if we get that log on the normal distribution, then inference is a lot easier, right? So basically, as it's saying down here, is that the MLE there's no closed form solution. And then what's being pictured down here is basically a probabilistic, a PGM, so probabilistic graphical model of the actual Gaussian mixture model, what we're trying to learn. So you can see is that we have, essentially we have our latent variable, latent binary variable here. We have a prior, so this is what it means by the arrow. So we have the prior with the coefficient pi for each, for latent variables. And then basically the latent variable then influences the actual feature observation, x. And x, specifically in the likelihood here, it has two coefficients. So it has pi and also sigma. And then this right here, again, just to review, this is plate notation. So this means that by denoting this, by surrounding this by a plate and then denoting it by n, this means that we have n of all of the parameters inside of this actual box. Yeah, and further specifics are beyond the scope of the course. Yeah, so even though MLE is, it's not, we don't have a closed form and stuff, let's just pretend like we did. Even if we did, we face additional problems. And then in particular, as we know, which we've said time and time again, is that we take an MLE, so maximum likelihood approach, is that we will be prone to overfitting, right? And that's usually why we do Bayesian, is that we introduce a prior, so then we end up regulating our actual model somehow, and we can prevent this overfitting. With mixtures, it's especially prevalent. In the sense is that what can happen is that you can basically have mixtures that get assigned to a single data point. And then if I'm just assigned, if this mixture is assigned to specific data points, this is kind of illustrated here, is that maybe I have one mixture, so I have a mixture of two Gaussians, maybe one Gaussian handles, so I guess this is, 1, 2, 3, 4, 5 points here, and then the second Gaussian just handles a single point. And basically what happens is that this right here during training, this will basically go right into like a delta function. So basically it's just a single point, and what happens is that actually this drives the variance down to 0, right? So if I go to the delta function, I have 0 variance. And what happens is that when I evaluate our actual Gaussian here is that it just, boom, the probability is infinity, right? Gaussian PDF, if I go to the delta function, basically all the area has to fit into like an infinitesimally small width, right? So the probability skyrockets. And you may say, okay, well, this maybe is, an extreme example, but let's say in the unsupervised problem, right? So I don't know how many mixtures there are. And let's say I have 6 data points, right? And let's just say that I just start off and I naively, I say, okay, let me fit 6 Gaussians to 6 data points. That's going to immediately overfit, and my model's going to blow up. So basically, that's really not good. So yeah, and one can basically also use the map estimate, so we can introduce a Bayesian framework. Additionally, we can, if we're dealing with, we can also prevent it by initializing, improving the initialization of these mixture models. This is kind of a recurring theme. These models are very dependent on initialization, just because of the way that they're being solved. You can arrive at potentially different solutions. And as we say here, in this case, the MLE cannot determine the number of K components. So as we say here, the higher the K, so it's like the example I gave, the higher the K, the higher the likelihood. So until you keep increasing the K until your K matches the same number of data points, right? Your likelihood estimate is going to keep increasing. And that's not a good thing, because essentially that's the true definition of overfitting. So this will not be the case in Bayesian framework. Go figure. And then another issue which we'll kind of retouch is the identifiability problem. So I won't talk about it too much here since we'll revisit it. But the idea is that in this case, I don't actually know when I train a mixture model, I don't know what actually represents mixture 1 and what actually represents mixture 2, because they can basically flip-flop. And as we say here, gradient optimization can be used for maximizing likelihood here, so you can go like a Robbins-Monroe algorithm. However, in this case, we'll concentrate on E&M because E&M, expectation maximization, is a particularly powerful method for doing mixture models. Okay, so E&M for just Gaussian mixtures in this case. So without looking at what exactly expectation maximization, looking at it from a broad perspective, we'll first just kind of talk about how do we apply it to Gaussian mixtures, and like I said, then we'll kind of revisit it in more of a broad and more general lens. All right. So the idea with E&M is that essentially we have an iterative optimization method. So what we're going to first do is that essentially we're going to, so right here, this is our law of likelihood again, so calorific L, and we have the summation over data points, and we have inside the summation of each component, right? So this is P of X. All right, so if we take the derivative of this law of likelihood with respect to mu, so inside, so one of our hyperparameters, and we set it equal to 0, we end up with the following. And we can see here, so if we take the derivative, ignoring all the algebra, and then adding in this particular component, which is right here is the Gaussian of this particular class, right? So we've multiplied on top, we multiplied down here on bottom. Basically what we end up is we end up with the definition of these responsibilities. And I guess further simplifications, we can arrive at the following. So essentially by, taking the derivative of the following, we can end up with responsibilities, which are represented as gamma down here. We then have 1 over the Gaussian here times the derivative of the Gaussian, which ends up being the following over here. And then essentially we're able to arrive at a potential closed form for mu. Now, the catch here is that essentially you would have to know gamma, right? So this implies, so basically what we've done is that we've taken a huge chunk of this derivative here, and we basically removed it. So we said, okay, let's just assume our responsibilities are known, okay, and then just work around that. And that's what we say here is that this is, even though, assuming these are known, it's closed form, but in reality they're not known. So basically the interdependence of mu, so our parameters of our likelihood, and then also these responsibilities, which is basically a function of our mixing coefficients and all of our likelihood functions. Basically, they interact with each other in a very complex way. And then say down here, the responsibilities basically represent posterior probability. So they're bringing influence from all of the data into the specific mu term. So the breakdown of this is essentially, so E&M, so the E step, so step 1, is that we're going to assume all the parameters. So in these cases are hyperparameters of the actual model. So these are my pi's, my mu's, and my sigmas. We're assuming that they're fixed. And what we're going to do is that we're going to evaluate the responsibilities. Okay? Then what we'll do is that then we'll evaluate the responsibilities. We'll then assume that those responsibilities are true, and then we'll revise our coefficients, right? Because on this previous slide, I said if we assume that these responsibilities are fixed, we can evaluate from mu, and this is true for sigma, this is true for pi as well, as we'll see. However, I have to assume that they're fixed. So essentially what we have is that we have an iterative procedure. So we update our responsibilities, we then go and update our hyperparameters. We come back, we update our responsibilities, we then update our hyperparameters, and we jump back and forth, back and forth, back and forth, until hopefully we converge. So again, our responsibilities, again, they're given by here. So this is the actual, the probability of this particular, so we have NJ here. So these indices, this means for a particular data point, in a particular class, right? So, so it says, what is the probability of this particular data point? So given some data point, what is the probability of it belonging in a particular class divided by the total probability of it belonging in any class? So this is what we talked. So this is the E step. So this is step one. And to compute this, we have to assign all these parameters. We have to assign pi, mu, and sig, and we have to fix them. Yeah, and this is just talking more about the responsibilities, which we've discussed before, of essentially how they can represent the posterior here, which is precisely the responsibility. So in particular, it's P of J, so of a given class, probability of a given class, given, probability of a class given X. Okay, so we computed our responsibilities. We've just fixed all our parameters. We compute our responsibilities. Now what we do is that we go and we update our hyperparameters. So we have each one of these gammas we have. For each one of our mu's, so for every single class, we go and we update each mu. We then update each mixing coefficient here, pi, and then update each one of these sigmas. So just looking at these equations, so without worrying about like the actual derivation, because the algebra is straightforward. You just you take the derivative of our law of likelihood as we always do, right? However, the reason why we're able to take the derivative is that basically we have these guys are known, and essentially we're evaluating these for a specific class. But just looking at these forms, at the solutions, each one of these are very intuitive. You can see, for example, there's this mu here, is that we have the responsibility times each one of the x, right? So this is the summation over all of our data points, all of our features, and divided by the total number of data points. And basically what this is that this is essentially a weighted average, right? So if this particular x, if our one component, if component 1 really isn't too responsible for this particular data point, it really won't be considered a whole lot in terms of the mu for class 1. However, if this data point n is really, if class 2 is really responsible for data point n, this gamma will be closer to 1. So then it will be more influential. So basically, it's just we're doing like a weighted average. Similar over here, our mixing coefficients. This is again, we're just kind of taking the average of all our responsibilities. And then similarly, we see again this weighted average idea for the sigma here with our responsibilities, weighting each data point. Okay, and yeah, so this is just talking about I believe arriving at these equations that were on the previous slide. So again, this is the law of likelihood. So we're able to take the derivative of it, and then under the assumption that these gammas are known. So in particular, this whole term here is known. We can then essentially figure out what mu is in this case. Similarly for sigma as well. And then you have pi again over here. And then we can see down over here, so ignoring all this algebra, well, I guess the only important part, so when optimizing for pi, so for our mixing coefficients, is that we have to impose the constraint of the summation of all these mixing coefficients is equal to 1. We do that by means of a Lagrange multiplier here. We've seen this before. And then essentially once we have that, we can go and we can solve for what exactly, this our lambda is and everything like that, and go from there. And again, this right here, this is actually our responsibilities. And what we end up with is that we end up with the summation of our responsibilities for that particular class divided by the total number of data points. And basically, one way to interpret this is that this nk term here, this summation, is that basically these are the effective number of data points that belong to a specific class. So it says how many data points, how many observations are in charge of this particular class, over the total number, and that's the weight of that particular class. And that makes sense. If one class has 50 data points assigned to it, we should weight that a lot more than maybe one that only has 2. That's exactly what this does. So it makes sense. Okay, so an example of applying E&M to Gaussian mixture models. So this is just kind of like a pretty classical toy data set. So the eruption of Old Faithful in Yellowstone. And basically what this data is that we have the time during eruptions, and then we have the duration of the eruption. And if you've ever been to Yellowstone, they have a clock, and they can, well, at least when I've been there, they're able to predict this fairly well. So this kind of has a real application to it, because you don't want to keep all the tourists waiting. There's other things to go see. So basically the data looks like this, and just looking at it, again, incomplete data, we don't know how many classes there are, but just looking at it, as humans, we can immediately identify there's 2 core clusters here. So in terms of our Gaussian mixture, just looking at that data, we can make the guess of just say, okay, we're just going to use two mixture components. So in this case, we just initialize the 2 Gaussians. You can see is that we're starting off with just like a unit variance. So we just initialize unit variance circle, and then basically we initialize 2 random locations for the means. So again, our first step. So step 1, which is the E step. Basically, the idea is that we need to figure out for every single data point, we have to figure out what is the responsibility, right? First, we compute the responsibility, and we hold all of our hyperparameters constant. Then on the M step, the next step is when we revise our hyperparameters. So you can see here, represented here by the colors, is that we compute the responsibilities of each class. So you can see that data points towards the blue circle, which is our first component, our second component. These are, they have more responsibility. Blue holds more responsibility for these points. Red holds more responsibility for these points. Again, this is just kind of you're just going through your computing responsibility, and basically it's kind of like an average. Okay, end step. So now, with our responsibilities, so all of our data points are basically colored. The next step is that we need to revise our hyperparameters, right? So we fix our responsibilities, and we go and we compute our mu's, and we also compute our sigma. And you can see that after just one is that our Gaussians are basically updated, so they moved when they're originally, as opposed to their original locations. So the mean of the blue component is fitted to all of the blue ink as if the red ink does not exist. So you can kind of see here essentially what these are being fitted towards. They're fitting towards a specific color. So in this case, the blue is going to the blue responsibilities. The red is kind of floating towards this red region, this heavy red responsibility area. And then again, for the next step, for the E step, what we do is that we then go for every single data point, we then recompute the responsibilities. So we say, okay, now with our updated Gaussians, for each data point, what is the responsibility of both these components? And you can see it now we've updated here. So compared to this picture versus this picture, if you look at the data points, that now we have a lot more blue data points down here in the second cluster, and then up here where this red component is, that we have a lot more red and a lot less purple. And basically we can continue and iterate, so we can jump back and forth between computing responsibilities, updating hyperparameters, compute responsibilities, update hyperparameters. And as we go, you can see this is step 1, step 2, step 5, and all the way until step 20, until essentially we've sufficiently converged by some sort of criteria. So we said, okay, between updates, only our mean, our hyperparameters only update by a certain amount, and then cut off the algorithm, we're good to go. M step, cuts in. Yeah. So very nice. So this is showing, kind of the updates and stuff. So again, the posterior probabilities. So remember that basically the posterior is represented through the responsibilities. So that's what's given by this color shading here. So in each step, components in the border area, so this is blue, green, or yeah. So during the each step, basically in these kind of these buffer regions, these are basically considered like ambiguous points. So whether or not they belong to class, class red or class green, we don't really know. They could be from either. Yeah, and this is just a repeat of what we said before. Okay. So as we said, for Gaussian mixtures, because we have this log and we're taking the log of a sum of Gaussians, right? And in the sum, in particular, the summation is on the inside of the log. Okay, summation is on the inside of the log, so there's no closed form solution. So because of that, basically our responsibilities depend on our hyperparameters, and then our hyperparameters then depend on our responsibilities. So the idea is that we have to do some sort of iterative update to get this working. Yeah, update equations suggest a simple iterative scheme. More iterations are needed to converge in this particular algorithm than k-means, and then each cycle requires more computation. And then in terms of initialization, again, so initialization of these two mixture components are pretty important. They have to be relatively reasonable. You can't just place your Gaussians way out in the middle of nowhere and basically hope that they'll try to find your data through numerical nature. So usually it's common practice to run a k-means algorithm, so run a pretty primitive algorithm, and then use those estimates that you did, that you found, to basically initialize your clusters, and then you further refine with like a Gaussian mixture model in this place. So the premise is that even though that there may be a model that's cheaper but it's not as good, you can use that cheaper model to basically as a starting point, and usually that will be good to help get E&M into the right local minimum. And as we say down here, because this is an iterative method, E&M is not guaranteed to find the largest of the local maxima, minimizing negative likelihood, or the minimum local minima. Basically, there's no guarantees by this, and this is also because of that non-uniqueness property. In particular, with this is that just to emphasize this non-uniqueness is that if I initialize, so if blue is my component 1 and then red is my component 2, if I swap these, so if now blue was down here and red was up here, E&M, even though these would still be defined as blue is my component 1 and then red is my component 2, they would end up as basically the opposite locations in terms of how we represent them. I would now view this as component 1, I would view this as component 2. So basically, it's non-unique is basically the issue. So this is again showing the same algorithm converging. And we can see here average log likelihood here. So we want to maximize it, right? And you can see that it actually it very quickly updates. So it's able to have a huge improvement initially from our initial guess, and then it kind of slowly improves here. It's a little bit harder to see because of the scale, but yeah, there is slow improvement until basically it converges. Yeah, and this is further talking about initialization. Like I said, initialization matters, so you can use k-means in this case. Yeah, and then there's different methods. So it says here, speech recognition community, they incrementally grow Gaussian mixture models to the desired number of clusters of reach. So maybe you start with 2, then you add a 3rd cluster, you re-optimize, you add a 4th cluster, you re-optimize, et cetera, et cetera. So there's different ways, different techniques to initialize depending on the data you got. Okay, so summary slide. Gaussian of E&M for Gaussian mixtures. So again, we have 2 steps. We have an iterative procedure. We evaluate the responsibilities here, which is like the posterior. So this is the probability, given some observation, was the probability of it belonging in a particular class. And we have the M step. So this re-estimate the hyperparameters here. So we fix our responsibility, and we can recompute our hyperparameters, and we jump back and forth. And we already talked about this. Okay, So in the context of what we just kind of talked about, we just talked about E and M for just Gaussian mixtures. However, as you'll kind of notice is that, you know, E and M, expectation maximization, we didn't really even talk about an expectation. We didn't really talk about, I guess we talked about maximization of hyperparameters, right? So, you know, it kind of leads to the question, okay, well, why is the E step computing these responsibilities? Like, that doesn't make any sense. And then, you know, if you know, how can we apply this to more than just Gaussian mixtures? How can we apply this to different mixture models? How can we apply this to Bayesian regression? How can we apply this to, you know, mixtures of Bayesian regressions? And the answer to that is basically to take the more general latent variable viewpoint of E&M. So yeah, so the more broad idea is that essentially we want to maximize the marginal likelihood of the observed data. And in here we have some sort of, in some sense, some sort of mixture. But basically we have, so we want to maximize the probability of X, our data, given some parameters. And then, but how we're modeling this, we're modeling this in terms of X and also this latent variable Z. So this joint here. And this right here is, you know, this is marginalizing it out. However, you know, this is very similar to Gaussian mixture of essentially having this summation inside of the log basically makes the computation of the MLE directly, you know, intractable. So yeah, so the idea is that now we just have a very general latent variable. And so now, if we look at E&M, so the expectation maximization algorithm, through a latent variable perspective, we have two very specific steps. So the idea with the E step is that we use our current parameters. So again, so theta in this case, these are like our hyperparameters of our likelihood. So in Gaussian mixture, this was our mu's, so our means, our standard, our covariance matrices, our mixing coefficients, right? And then our z's in the Gaussian mixture happen to be our responsibilities. So the idea with the E step is that we want to use our current hyperparameters, so our current theta, so in this case it's denoted by theta O, to basically compute the probability of our P of Z given our data and then also our hyperparameters. So this is like the posterior, right? So this is the posterior Z. And then basically take the expectation of it. So we want to take the expected value of these actual Z variables. Yeah, and then the M step, so the M step is very similar, is that the idea is that once we've computed or once we've gotten an estimate for what these Z's are, we want to update our hyperparameters here. And then basically we check convergence, that we iterate over and over again. All right, so we a little bit more straightforward, I think, in the next couple of slides. As it says here, is that if you take a Bayesian representation, so in the M step, right, we're updating our hyperparameters. So we're taking a very MLE update of the hyperparameters. We're maximizing basically our likelihood. We can introduce a Bayesian representation of on these hyperparameters. So in this case, we can introduce additional priors on these theta. So again, these will be priors on your means, your priors on your standard deviations, and stuff like that. So this algorithm can also be applied when unobserved values correspond to missing data, but only if the mechanism causing the values to be missing does not depend on the unobserved values. Okay, so I think the much better idea is, again, is just kind of see this latent variable, this idea of we have some latent variables. What we do is that we compute the expectation. So we take the expectation of these latent variables, the posterior of these latent variables. We then take those expectations and we maximize the hyperparameters, and we repeat the expectation step over and over again. It's very easy to see this idea pop up in our Gaussian mixture. So revisiting this in terms of this latent variable idea, we can see is that we have a joint here. So we have the P of X comma Z is equal to the following. So you can see here again we have these binary, and these are basically these binary switches, right, that are turning on and off depending on the class that you want, and it's equal to the following product. So for a particular class, right? It's just going to be pi of k and then the likelihood for that particular class. So now if we take the log of this following of the joint here, basically we end up with the following. And what we can see, what's interesting is that because we're also doing the probability, because now this is not the log likelihood of x given theta, this is the log likelihood of p of x and z, is that now what actually happens is that now the log is actually being able to be drawn into the actual the distribution here. So we no longer have the sum inside the log. And that's because we're using the joint. And that's what we said initially when we introduced these, right? These will simplify our inference. So we can see that directly here. So now we have this product, but we're going to take the product out in terms of summation. So now we have a summation over the classes. We have a summation still over all of our data points. And now we have the log of our interior. So this is our mixing coefficient and our likelihood, and also our binary variable here, which was up here in our exponents, and we pulled it out here because we have the log operation. So by knowing z's, basically the sum is now on the outside of the log. So as we say here, if we know the z's, things become a lot easier, but this implies that we know the z's. Okay, so this is just talking about again. So this is way. So implying that we know the actual z's, right? Figuring out what exactly the maximization of our mu's, our sigmas, and our pi's is fairly straightforward. So spoiler alert, the z's are the responsibilities. If you think about what we discussed on previous slides, if we know those and we fix those, we can then compute our hyperparameters. That's basically what we're saying here. So these are basically working out, maximizing it. We can see again, we have our pi is equal to the summation of the z over n here. Yeah. So the idea is that but we don't know these z's, so we had to figure them out. And again, so this is the E step. So basically what we talk about things in reverse, okay? So this previous slide is like the maximization step, is that we're trying to maximize this joint here, given a particular z. So we assume that z is known, and we try to maximize the hyperparameters around it. This is the E step, so it's like step one, and the idea here is, again, we're taking the expectation. Expectation of our latent variable is E step. And expectation, by definition of expectation, right, is the marginal of x times p of x, right? So we have a summation. So if our z's are binary, right, they can only take two values. So the marginal is discrete. So you have a summation of what is the probability of z is equal to 1 given some x times 1, so this is the value of z, plus the probability of z is equal to 0 times 0, so this term just goes away. Now, if we figure out what exactly this is right here, you know what this is? This is like the posterior from before, right? So this is actually ends up being precisely the responsibility right here. So we're able to directly evaluate this. This right here, this is just use the Bayes theorem, right? And we end up with exactly the responsibility. So what we end up finding is that the expectation of our z, the expectation of these binary variables, is actually given by the responsibility precisely. So now essentially what we do is we have our two steps. We have the expectation of these latent variables, which is computing the responsibilities, and we maximize the joint of the mixture model in the M step. Yep. So again, here's the PG, the probabilistic graphical model. We see it on this before. Yeah, and this is just kind of showing you of essentially, this is kind of like the more, with the latent variables, taking the latent variables inside. Again, because basically these latent variables are binary, even though we have this product, the idea is that this is only active, this whole thing is basically, it's just the internal component when k prime is equal to the k that you're concerned about. So this is just like the more rigorous way to write it, is write it as a product of the total components with the indicator variables, but these are only on for the specific component here. So so yeah, that basically just ends up being the exact same thing. It's just a different way to write it. So yep, again, like we said before, E step expectation of our latent latent variable Z is our responsibilities, and then the M step is that we want to maximize. So again, we're trying to maximize the joint, right? The joint, because we assume that Z is known, and then we can simplify the arithmetic, right? So originally, again, just to emphasize, originally if we just took P of X, so if we didn't have this Z, we would have this summation inside of the log, and we would be stuck. But because we're taking it of the joint, and we're assuming that Z, that we're using the expectation of Z, essentially we can optimize this very easily, or find the maximum of it, just using like a maximum likelihood approach. Yep, and this is all saying the same thing. So yeah. Yeah, so this is again another summary slide of basically everything that we've done. Okay, so this is a so if we compare the E&M algorithm, so if we use the E&M algorithm for a Gaussian mixture model, and we compare it to k-means. So k-means, we just try to, we try to find, we just try to cluster based on nearest neighbor, right? Basically what we find is that k-means is a certain limit of E&M for Gaussian mixtures. So the idea here is that E&M is a much more broader algorithm than k-means. So k-means is basically a special case. And let's see here. So if we consider a Gaussian mixture model, all with the same, so basically all with the same standard deviation in this case. So you can see here is that now what we have is that we have a fixed standard deviation for each one of these Gaussian mixtures. So it actually does not sigma k. It's just a constant. And basically, if we work out the responsibilities, and then if we draw, if we take this standard deviation, we drive it to 0. The idea there is that we end up at the k-means method, at the k-means algorithm. So within basically the limit of bringing the standard deviation down to 0, we arrive at what is the k-means method. Because essentially, well, even with a constant standard deviation, the only thing you have to optimize is basically the mu. So you can think, intuitively, k-means, I'm just finding the means of all the cluster, the ideal means. This is essentially what it's doing, is that if you fix it and you make it negligible, you arrive at k-means. Okay, so moving on. So another mixture model that we'll look at is the mixture of discrete binary variables. Or Bernoulli mixture model. So the idea here is that very similar, is that now what we have is that we have a mixture. So this is actually our mixture distribution down here. So again, we have our mixing coefficients, and we have our likelihoods here. Our likelihoods this time are given by the Bernoulli distribution right here with high parameter mu. Yeah, so clearly here we have two high parameters that are unknown in this case. And you can see once again, what does it say in this slide? However, if you took, so if we say we want to maximize this, we want to maximize the likelihood, right, and we took the log, we would again have a summation inside the log. So this would be inside the log, and we would be stuck again. Okay, so just as like an example, so it's kind of like a teaser. We'll come back to how this actually works. But basically, with a mixture of Bernoullis and the MLE, a good example that this can be applied to is actually MNIST. So the idea is that with these MNIST images, with these handwritten data, right? So it's just images of handwritten numerics. Basically, I can represent these, each one of these pictures, I can represent them as a vector. As a vector of binary variables, right? So they're 1 for white, 0 for black, and then depending on the numbers, right? So if it's for, the numeric 1, it should have some sort of probability of certain pixels being white, certain pixels being black. Similar for other numbers such as 6, 0, etc. So if we fit the model that we're going to talk about to this in this data, essentially you can see that it arrives at some interesting results. Essentially, this is showing, so in this in itself, so in this case, basically we fitted, 10 different clusters to MNIST, which that makes sense, right? MNIST, it's 0 through 9, so we should have 10 different clusters fundamentally, right, for each digit. However, we can see is that when we fit this using MLE, is that we can arrive at some of essentially some get repeated. So, for example, we have multiple 9s. So these are basically showing the basically expected value for each specific class, right? So this is the learned classes that it's found. And you can see that some, it's found 1, but it also found multiple 1s. Maybe this is kind of like a 7. But you can see like some of them, this is almost like a mix between a 7 and a 0. So it does like a halfway decent job, which we'll talk about how this works and stuff like that. But it's just like a little teaser of what we could actually apply this to, something other than hot water coming out of the ground. Okay, so once again, we have the log likelihood of our mixture distribution. Like I said, we end up with this summation inside the log. So basically, we don't have a closed solution expected. So what's our seeing that, we want to apply the E&M algorithm. We introduce, so right, E&M functions on latent variables. So we have to have a latent variable defined because, right, the first step is that we want to take the expectation of the latent variable, and the second step is that we need to maximize our hyperparameters around that expected value of our latent variable. So you have to introduce a latent variable somehow. And similar, just like our Gaussian mixture models, that we introduce a binary, right, a binary k-dimensional latent variable, which basically we can see here is that, again, we can represent these in terms of these exponents right here, these two z's, which again, these are basically operating as indicator functions. Does it belong in class K? Okay, this will shut off everything that's not class K, and it will just be pi of, pi k. Yeah, so as we know, now if we take the joint, so now we have the joint of our observations and our latent variables, what happens is that now if we take the log of this, right, so if we have the log, basically we see that we can get the log into the summation. So now the summation is on the outside. So you can see here is that we have the log of our mixing coefficient here, pi, and we have the log of our Bernoulli likelihood, right? So yeah, you can see like the x's, these x's were, this was originally the exponent, this was originally the exponent, so it's like the Bernoulli distribution right here. Yeah, so the first step is to take is to find the expected, so take the expectation of the complete data log likelihood with respect to the posterior distribution of the latent variables. So this is seen here. Basically, the expectation of z is again essentially being represented through our responsibilities. This is exactly like the Gaussian mixture models. But basically, now we have a different likelihood. So again, this is actually found out through Bayes' rule. So if you remember before, if we just take the expectation, we want the probability for a specific z. Let's say this is zk or something is equal to 1. We want to find the probability of zk is equal to 1 given our data and our hyperparameters. And that's found out through Bayes' rule, which is seen here. So this is basically the probability of x given our k, and then over the entire probability of x X here, right? We're marginalizing over the classes. So this is just found out through Bayes' rule. But this is essentially exactly what we saw for the Gaussian mixture model. These were Gaussians before. Now they're Bernoulli distributions. So that's very nice. The expectations here. Note the responsibilities come through as the following terms. Yeah, and as I said before, NK, so the summation of the responsibilities is basically, you can interpret that as the effective number of data points for that specific class. Okay, M step. Again, so we've computed our responsibilities. That's our expectation of our latent variables. We take those, we plug them into our joint, right? So our joint here. And then once we have that, we can then start taking derivatives. So in this case, you can see here is that now we know, so we know this term. We can now take the derivative with respect to our hyperparameter. So we take the derivative with respect to mu. We take the derivative with respect to, so you can see this is the definition of mu here, which, so we look here, right? So again, mu, and this is again some of the Gaussian mixture. So we're seeing a weighted average for this specific class, right? So we're seeing these are being weighted based on the responsibilities, which is something that, you know, intuitively makes sense. And then again, once again, pi, our mixing components, we have to do the same thing that we saw before, is we have to impose a constraint, which is the sum of all our mixing components have to equal 1. That's to make sure that we are still a probability distribution. We do that through a Lagrange multiplier, ignoring all the algebra, because it ends up being exactly the same thing, which is, again, is just the effective number. So again, NK, this is the sum of the responsibilities, effective number of data points for that specific class, divided by the total number of data points. And right, that makes sense. More data points in a specific class, the more weight it should have. Because during sampling, so if you think about this in terms of sampling, you know, if 50 points belong to one class, 2 points belong to another class, I want to be sampling from, you know, the first class with 50 points 50 times compared to like the one that the other ones for, you know, I just want to be sampling twice for maybe every single, you know, 52 samples. So yeah, so this makes sense. Yeah, so an interesting note about the Bernoulli distribution. So in contrast to the mixture Gaussian, so remember with the Gaussian mixture model, we had this problem, this potential issue of essentially when you overfit with the likelihood, your variance goes to 0. And what that causes is that results in your the PDF of the Gaussian to skyrocket. It basically goes to infinity. With the Bernoulli distribution, we don't actually have that problem. Because basically we're limited. It's limited between this 0 and 1. So we can't actually, we don't have this issue with it. However, basically the likelihood function can go to 0. So in this case, basically the problem with this mixture of Bernoulli distributions is just like, if you guys remember, 3 weeks ago or something like that. We talked about, when I was in here talking about discrete generative models. We talked about a Bernoulli model for modeling coin flips, right? And the idea there, something that we brought up was essentially, if I observe all heads of a coin flip, I observe 3 coin flips and I observe all heads, right? And I do an MLE fit on all of those. Basically, it will say the probability of getting tails in the future is 0. Okay, and that was known as the black swan paradox. Essentially, you have potentially unobserved events, which may or may not be rare. And so this has the same issues as a situation. So yeah, so assuming you have enough data, you don't really have to avoid that, or you can introduce a Bayesian prior. So this is showing the example of the handwritten digits. So the MNIST data set, so we will illustrate this Bernoulli mixture. So we convert, like I said, we convert the images, so the images of the handwritten number into basically a vector of zeros, 0 to 1. Okay, setting all elements whose values exceed 0.1 to 1. So basically we set them, so we model them between 0 to 1. Yes, we have 600 data points comprising of so we just take the 2, 3, and 4 digits, so rather than all 10, we have 3 Bernoulli mixtures. So we have 3 Bernoulli distributions. So the ideal case is that we end up with a Bernoulli distribution that represents each number, so 2, 3, and 4. And then basically we run 10 iterations of enum, initialize. We initialize our mixing coefficients to just 1 over the number of classes, so we just uniformly weight everything initially. Makes sense. In terms of mu, basically we just randomly initialize those. Choose uniformly between the range of 0.25 to 0.75. Okay, so after doing that, MATLAB code is here if you're interested. So these are some of the samples, so some of the input data, and basically these are the learned clusters. These are like the expected value for a particular class, for each of the 3 classes. And you can see for each class it was able to figure out, okay, here's the probability of 2, right? Here's the most likely probability of 4, here's the most likely probability of 3. So bottom 3 images showing the parameters. This is the expected value, or mu in that case, of the 3 components of the mixture model. And then the last image, we fit a data set using a single multivariate Bernoulli distribution. So this is showing if I took this data set and I just used one Bernoulli model, and that's it. And as you can see, basically what happens is that it just ends up morphing 2, 4, and 3 into basically an 8-looking number, because I just have one. This is basically a mixture model, just one class. So you see it's not very good. Yep, so in summary, very similar to Gaussian mixture model, but basically now my likelihood is this Bernoulli distribution here. And again, we have the E step, which is the expectation. We find the expectation of our latent variable Z, which happens to be the responsibilities. The responsibilities are basically the average or basically it's the posterior of that particular latent variable. And we have the M step. So we fix our responsibility. So we take the expected values of our latent variables, we plug them into our log joint, and then we take derivatives of the log joint and we evaluate for hyperparameters, which in this case we just have pi, our mixing coefficient, and mu, this is the hyperparameter of the Bernoulli distribution up here. So pretty straightforward. So we can extend this, so we can do some additional extensions here of our Bernoulli distribution. So if you remember back, lectures ago, a long time ago, basically what we can do to try to prevent these potential issues of not seeing data, MLE overfitting, still a problem in mixture models, we can introduce a prior. So in this case, we can introduce Dirichlet or data priors onto our likelihood to basically try to throttle this mu parameter so it just doesn't go down to 0. Kind of messed up slide. Let me see here. Yeah. So the idea here. Yeah. So nice thing. So ignoring this messed up math. Basically, as we mentioned before, with the expectation step, the expectation is basically unmodified because the computation of the expected value of the latent variable or responsibilities doesn't really get changed. The only thing that really changes is basically the end step. In the case of the prior for mixture weights, one method that we can use a Dirichlet distribution for those. So basically the map estimate becomes the following. This is actually very similar to stuff that we've seen before, in particular with the Bernoulli beta models. Basically, for uniform prior, by definition of Dirichlet prior, we use Dirichlet in this case because Dirichlet can span, it can span, if you have 3 components, it can span that space of 3 components, it can span the space of 4, or simplex, if you're into that jargon. So for a uniform distribution, alpha k for each component is equal to 1. So essentially what we end up getting is that we end up getting something along the lines of basically like kind of +1 smoothing in some sense. So basically this prevents it going down to 0. That's what the, yeah, and this is the exact same thing that we just saw. Yeah, we can do the same thing for map estimates of Gaussian mixture models. I'm assuming he's going to revisit. You guys haven't seen fully, no. He'll probably revisit this for the fully Bayesian Gaussian mixture model in a more complete lecture. This is a normal inverse Wishart function, but you can basically do the same thing. So you can place priors. So now we have some priors on our mu's. We have some priors on our sigmas. So the prior on mu is a normal distribution. The prior on our sigma, our covariance, is a Wishart distribution, which basically that's just a good prior if you need a semi-definite positive matrix. Which all this will be talked about more, I'm assuming, later in later lectures. So we're not going to spend too much time on it. But basically what this does, it allows us to regulate our hyperparameters. We can prevent overfitting. So yeah, so we can kind of see here is that our if we take the MLE estimate here, so in this case down here on the bottom we have the dimensionality of our given data, and we have the actual Gaussian mixture model, or the EM, the failure of EM to actually solve the Gaussian, to solve or converge properly, right? So basically to fail in E&M is basically it's put a Gaussian onto a single data point and it's just drove up the standard deviation, or well, basically lowered the standard deviation down to basically 0, exploding the probability. So as dimensionality increases, we can see that the MLE basically always fails at some point, and while the map estimate with additional regularization is trying to prevent that standard deviation from going down to 0, we can see that basically we can stabilize the E&M algorithm significantly. And that's kind of like the moral of the story. Okay, so just a couple more minutes left. We'll just kind of briefly talk about this. So an interesting application of E&M is also for Bayesian linear regression. So remember linear regression, we have some, let's see here. We have some basis functions here. We have some learnable weights that we're trying to find, right? We're trying to do a regression over some sort of function. And then for the Bayesian version, we introduce a prior onto the weights themselves given by this normal distribution. So that should all look very familiar. So the idea here is that basically, in terms of if you recall with Bayesian linear regression, we can evaluate what our weights are if we know what alpha and beta are. However, the problem is that there's no closed form solution what this alpha should be. And actually what happened is that you had to do an iterative procedure to actually figure out what these hyperparameters should be. Now this wasn't discussed in the context of E&M, but what's particularly interesting is that you can arrive at essentially the same solution by E&M, that's kind of like the merit of these slides. So our E&M, we have 2 different steps here. So the idea here is that we're going for the E step is we're going to compute the posterior distribution of W given a current setting of hyperparameters. So basically what this is saying is that W in this case is acting like our latent variables. These are our variables that we don't know and we're going to want to find what the expectation of them are. And then we have the M step, so with these determined, we take the expectation, we lock them in place, and we update our hyperparameters, and we iterate them over and over and over again. Okay, so basically this is essentially assuming that we have our posterior over W. So we've already derived this in the past, right? So this is from, I have the bookmark here. This is from Bishop chapter 3. You can open your textbooks and look at it. So this right here, this is literally the posterior of W. Okay, so you can see very familiar looking matrices here with the pseudo inverse here, our basis functions. All this is very familiar. Basically, the expectation of this, right? So, right, the E step is that we want to take the expectation of our latent variable is actually it's going to be this M. So this is actually like our M, our expectation. We know that, so we can do our E step, right? This is all straightforward. We've done this before. So now what we can do is that now we can plug this guy into our log joint. Again, our log joint. We plug it in, and we take derivatives with respect to alpha and beta. Then we can update our alpha down here and our beta down here. So you can see here that we plugged in this Mn, right? Expectation of our posterior over W. We plugged it in here, and now we're evaluating for alpha and beta. You see that these two are they're related, so we have to iterate over and over and over again. So yeah, so this right here, this is the result of, these are the updates for alpha and beta hyperparameters. This right here is what was derived. So if you actually go back in chapter 3 of Bishop, this is what is derived, just ignoring enum entirely. So in particular here, you can see is that we have, we have some sort of function, and in these lambdas here, these are actually the eigenvalues of basically actually this S matrix. Because I don't have a lot of time left, basically the philosophy is that what happens is that if we do this enum procedure, okay, so if we take the expectation of our weights, we plug them into our joint likelihood, we then update our hyperparameters, is that we end up at the same, basically in the same spot as what was just derived completely independently of ignoring enum or anything. So we just went back chapter 3. So somehow we just ended up back fully consistent with what we know Bayesian regression to be. And yeah, just like, key thing right here. So basically, like I said, is that these right here, these are the eigenvalues of, I believe this matrix right here. And actually this trace, right, the trace of a matrix, Sn, is actually just the sum of its eigenvalues. So you can kind of see how that's related there. So yeah. And yeah, then we can further apply this to relevance vector machines, basically just Bayesian regression with